Record. All right, so the session is being taped. There are a couple ideas that we had to do to complete. This is the notes that Shane sent to me. Shane's work is quite outstanding, as you can see. Diagrams are exceptional. But this is pretty much what you all copied down in class last day, with the exception of this, which I had to do for everybody to see. But this is the right-hand rule that deals with the direction of the induced current when there is a field and motion. All right? But pretty much all of this, including mutual induction, we had done in class, as well as the graphs dealing with mutual induction. We also went through the derivation of the equation for the EMF induced in a straight wire. There are 3 derivations in this handout, and the 3 derivations, they're based on the same principle. The key is to understand the underlying principle to the derivation rather than focus on the actual derivation themselves, because they look different. But the underlying principle is Faraday's law. It's the same underlying principle. Again, we have done this one already, BLV sine theta. We now want to look at this device here. This is called a homopolar generator. It's really a disk that is set in rotation. This is the axle of the disk. And this is a magnetic field that the disk is subjected to. Now, once the disk starts spinning, by magic, if you will, if you connect a voltmeter to the circumference, or anywhere on the circumference, and the other end of the voltmeter anywhere on the axle, you're going to develop a potential difference across this disk from the center to the outside. And that is because of the rotation. Now, why is it? How is it possible that this EMF could be generated simply by rotating a disk? Because clearly you don't have like a wire. But if you think about it, that disk is made up of a series of conducting strips that you can consider as wires. I have shaded one such strip to be able to complete our analysis. Consider this piece of this conducting strip. So this disk, sorry, this is a continuous disk. Consider this piece here. This piece is a conducting piece of material. In it, we have electrons. And when this disk is in rotation, it is as if this wire is spinning about and covering this shaded area. Everybody get what that? This wire, as this wire turns in the same way that in the previous derivation, we saw that this wire was sliding across and clearly cutting these field lines. Similarly, as this wire rotates about the pivot point, it will cut all of these field lines in one revolution. That point, I think, is simple enough for everybody to grasp, right? As the wire rotates, it is going to be cutting out the field in this piece. And because the wire is cutting the field, there's going to be an EMF induced across the 2 ends of the wire, which is exactly what this voltmeter is picking up. It's picking up the EMF, the voltage between the center and the circumference. Now, let's look at the derivation. To deduce why this happens, we consider a disk as being made up of a series of wires rotating in a magnetic field of strength B. As the wire rotates, it will cut the flux. When the wire rotates for one complete revolution, the flux would be cut. The flux cut would be all the flux passing through the area. So when this thing makes one complete revolution, the flux cut would be all of the flux in this area. All right? Now, what area are we talking about? That area, this circle is of radius r. So that area is simply pi r squared. And therefore, the amount of flux that is cut, delta phi, is equal to B, the flux density, by the area. We know phi is equal to BE. All right, we good with that? Any questions? We saw this already, that phi, by definition, at the very beginning of this handout, we talked about magnetic flux. All right? And we talked about phi being equal to BE. This area is the perpendicular area. All right? So that's all I'm using, that the amount of flux that is being cut when this disk rotates. The amount of flux phi cut when this disk rotates is the field strength multiplied by this area. Now, how long does it take for one complete revolution? The time for one complete revolution, which I'm calling delta t, is really the periodic time of rotation. And we know that periodic time is simply 1 over f. Now, we have two pieces here. We have delta phi, the amount of flux cut, and we have the time it took for the flux to be cut. Now, if you recall Faraday's law says this, but mathematically, we said that Faraday's law says, I do have it here. Here it is. That Faraday's law says that the EMF is equal to minus n delta phi over delta t. Now, in this case, n is 1, is the one strand of wire that we are considering rotating. So n is 1. So that the EMF is minus delta phi over delta t. Again, EMF is, I'll put the minus sign, but the minus sign is just for polarity, so I don't want to get messed up in the equation. The EMF, the magnitude of the EMF, I'll put it here, according to Faraday, comma, the magnitude, of the EMF is, right? According to Faraday's law, the magnitude of the EMF is delta phi over delta t. Delta phi is b by pi r squared, b by pi r squared, and delta t is 1 over f. So this is the expression for the EMF induced as a coil rotates in a magnetic field, the EMF induced across the ends of the coil. Now, there is a commonality in these two derivations. So what is the commonality? Both equations stem from the laws of electromagnetic induction. That is, E is equal to minus n delta phi over delta t. When we did the first derivation, we did the same thing. E is equal to minus n delta phi over delta t. Again, n was 1. And we had worked out that delta phi was the amount of flux cut in 1 second. And that was the flux in this area of area LV. And that's how we got BLV, all of it stemming from this simple idea. All right. And again, when we're talking about this EMF induced in a spinning disk, we're using the same form. I could put the negative sign here just to bring in the polarity, but I'm just concerned with the magnitude right now. Are we okay with this? Everybody clear on this? This equation? Any questions? If you have a question, you can ask it. You can unmute your mic and ask the question, or you can type the question. In 5, 4, 3, 2, 1. Good. Done. So that's one idea. Now, this same idea, the same kind of question came. Did I give you all a handout with questions on electromagnetic induction in our last class? Keep electromagnetic induction questions. Okay, good. I want you to, I'll put it on my screen, but I want to focus on a question that is based on the same principle that came in the CAPE exams, right? So I'll just find the question very quickly with me. If you can find that handout, you'll have it in front of you as well. Right then. Oh, I know where it is. There we go. This is the question here. First question. All right, so the question says figure 5 shows a long solenoid. So again, this solenoid is wound. This is a cylindrical solenoid. And you basically have a current being supplied. You can vary the current, but a current being supplied to flow in the solenoid. Now, from what we know, if you have a current flowing in the solenoid creates a magnetic field. Let me just annotate. Oh crap, that's not the way to do it. Hold on. I need to take it out from this program because this program makes drawing very difficult. So I'll just very quickly copy this into a better drawing program. So that is our, the coil. And let's look at the coil. The coil is creating a magnetic field. I'm going to try to draw the magnetic field that would be set up inside the coil. The direction is just somewhere. Direction is, we'll figure out the direction of it. Could anybody tell me where the North Pole is, on the right-hand side or the left-hand side? You're supposed to know this. Anybody can tell me where the North Pole is, right-hand side? You can't see the question.
Sir,
Yeah,
the screen is first, and I can't see anything. It's still on the electromagnetic induction my notes picture.
All right, well, the question that we're looking at, what's happening is probably your internet connection is a problem. Anybody having that same problem, or is my internet connection? One of the two.
Could I hang up and call back probably?
Well, you're not calling. You can come out and rejoin, I suppose. Anybody anybody else having that same problem? Can you see my drawing, people? So Vishnu, you're seeing the drawing, right? Everybody's seeing the drawing? All right, good. That's what I mean. I need to know if you're seeing it. Okay, it's probably the internet connection that that's creating the problem. But I'm going to step on. Okay, you can see now, Kiran. Wonderful. The thing is, the question I asked is, so which side of this solenoid is the North Pole? Could anyone tell me the right-hand side or the left-hand side? Is the solenoid, is the North Pole going to be here, or is the North Pole going to be there? The right-hand or the left-hand side? Not everybody answer at once, please. Just one person at a time. Okay. All right, the rule we're using is called the right-hand grip rule, right? So let's apply the rule. Right-hand grip rule. The fingers must point the direction of the current. So the current is going up here, and therefore going up in each one of these strands. Right, that's right, it will be to the left. The current is going up in each one of these strands, and if you were to grab this, then the fingers of your right hand will be pointing up, and it means the thumb of your right hand will be pointing to the left. So the North Pole is to the left. Final word. So that's how the magnetic field is going to look like. Now what we know is inside this coil, the magnetic field is really going to be a uniform field, right? I just want to kind of paste it in here. So we can see the magnetic field is going in that direction. Right. Just want to put this in a different layer. And move that around. Oops. Sorry. Bang. Right. Just give me just the software doesn't happen immediately with the software. But what we can get out of it is quite amazing. So just give me a little more control. Right. So we can see the field. All right. So we can see this magnetic field, and this magnetic field is pointing to the left. And what they try to draw here is, you see this line here? This line is a line connecting to the circumference of the disk and this line is being connected to the axle of the disk. The disk is shown as a rectangle here, two-dimensionally. And here you have this axle that is connected to a motor that's spinning this disk, right? So let's take away the things that we don't want to see, which is this. Which is this. I don't want to see that. What I want to see is I want to see that disk. So I'll put that in another layer. I'll make that disk in 2 dimensions. The disk will simply be a rectangle. Give it some size and some color. So this is my disk. Well, a little bit. Let's make it smaller than that. Right. So that is the disk. This disk is in a magnetic field and the disk is rotating. All right. You have a connection. I'm going to be loose about this. I'm not going to try to draw this too neatly. You have a connection to the top of the disk connected to a voltmeter. All right. And a second connection connected to the middle of the disk where the axle is. So these are the 2 connections, and this disk is in rotation. So this, zoom in, right? This question is exactly what we've been just learning about, which is, if you have a disk rotating in a magnetic field, there's going to be a voltage generated between the center of the disk and the circumference. That is the concept. Again, we can bring back up the other part of the diagram. That's the complicated part. All right, that's all the drama going on. And you can see what I was saying. There's a connection from the top of the disk to one end of the voltmeter, and the other connection from the bottom of the disk to the axle, to the center, right there, right? So I'm going to hide this. I don't like this diagram because it just confuses. That's the simplicity of it. That's it right there. And it is reducible to the same question we've been thinking about, the same idea, the same theory we've been studying about. It is this theory right here. All right, so the question is about this whole theoretical dimension. Now, let's continue looking at the question. What is this question asking us then? Now we know what is going on. Explain why an EMF is generated between the axle and the rim of the disk when the disk rotates. Why is an EMF generated? Well, the basic idea here, why an EMF generated, is you have a conductor moving in a magnetic field, and field lines are being cut. That's why an EMF is generated. You can take that down. What you have was, why is an EMF generated? The conductor, the disk, is moving in a magnetic field, and the flux is being cut. And of course, according to Faraday, an EMF is going to be generated. First part done. Next part. The disk has, so those of you not, because of the internet connection, some people might apparently get the images a little bit later than others. Just hold on and hopefully you'll see it. I'll try not to change screens too rapidly. The disk has a diameter of 40 millimeter and rotates at 9.5 revolutions per second. Just make this a little smaller so you can see the equation. See both handouts at the same time. So they're giving us, yeah. They're telling us that the disk has a diameter of 40 millimeters and rotates at 9.5 revolutions per second. 40 millimeter allows us to find R. R is therefore 20 millimeters, right? So write that down. You have a piece of paper. I'm dictating. It's difficult for me to write with this software. So if you can help me by writing that down, the first information we have is that R is equal to 20 millimeter. 20 millimeters, 0.02 meter. We want to go into, work it in meters one time. R is equal to 0.02 meter. The second bit of information they gave us is that 9.5 revolutions per second. That is frequency. F is equal to 9.5. So far, so good. So when you look at the equation for the EMF, we already have R, which is the radius, which is 0.02 meter, and we already have F, which is 9.5. We're good so far. The missing bit is B, and let's continue reading. The solenoid is 0.08 meter long. It has 160,000 turns and carries a steady current of 5 milliamps. All right? Well, we didn't present the question. The first part of the question is what I'm going to do first, which is now. What is the field within the solenoid? The field within the solenoid is given by the equation, I'll just pull this up so I can write. Given by the equation, B is equal to mu naught N I. N is a number of turns per unit length. So it is also reducible to the equation mu naught capital N, the number of turns total divided by the length of the solenoid multiplied by I. Now in this question, they gave us some values. They gave us N as 160,000. They gave us 160,000. They gave us L to be 0.08. They gave us L to be 0.08. And they gave us I also. I is 5 milli, which is 5 by 10 to the minus 3. So immediately we know this is 4 pi by 10 to the minus 7. Mu naught is equal to 4 pi by 10 to the minus 7. So we really have everything here to be able to get the first part of the question out, B, the magnetic field within the solenoid. All right? And the next part, it's pretty straightforward. That's what we're working. The magnetic flux cut every revolution. How much flux will be cut every revolution? Again, the amount of flux cut, phi, is equal to BA. Phi is equal to BA. We just got B. And we know that A is equal to pi r squared. Pi. And we worked out, we said the radius was 0.02 meter. We good? So from there, we got the B, running this calculation, we plug it into here, and we multiply by the area, which they gave us enough information to find already. And therefore, we can work the second part. The magnetic flux cut every revolution. Why? Because the amount of flux cut every revolution is the amount of flux in this entire area. Because when this piece of wire moves around, all of the flux inside the shaded area would be the flux that would be cut. The final part is the potential difference maintained between the rim and the disk. Once you get the amount of flux cut every revolution, you just have to take this. Again, you don't have to memorize the derivation. The way they set up, they structure this question, when you have to, we know that EMF And I'll not call this phi, I'll call this delta phi. This is delta phi, the amount of flux cut in one revolution. The EMF E is equal to that delta phi over the same story again, right? Same story, no different story, delta T. That's what the EMF is equal to. And it is equal to BA, which is all of this, divided by what is delta T? 1 over F, which is 1 over 9.5. So you're taking the answer you get from here, after you multiply out this, you're taking the answer you get from this calculation here, and you're popping it here, and you're just dividing it by delta T. And lo and behold, you can work out the entire question in one go. Screenshots if you wish. Of course, this is being taped and stored in YouTube, but yes, Vishnu, shoot. You can ask questions so I'll hear it, and everybody can hear it at the same time.
Isn't EMF N beta on dt?
Absolutely. So
you need to multiply by N.
And what is N?
160,000.
No.
Oh.
That 160,000 is the number of turns in the solenoid. That solenoid is not what is being cut. What is being cut is the disk. You understand that? The solenoid, the 160,000 turn, its function is just to create the magnetic field. The function of the disk is to cut that magnetic field.
Okay, I understand.
All right. So this 160,000 creates this field, and as this disk rotates, that disk. And what am I talking about? We're talking about this disk here. This disk, this arm of this is one turn, if you will, is what is rotating. I mean, when you connect, this is an interesting question though. How come, I mean, somebody could argue and say, well, sir, this disk is really made up of a whole set of these same lines going around, so that's your N. And the answer to that is, no, that's not the N, because when you make a connection, you make a connection from one point on the center to one point on the circumference, and therefore you've isolated one strand. Getting that? You can argue that you have 100, you can probably have 100 or 1,000 of these spokes, all right? But my answer to that would be, when you make a connection, you're making a connection from one point on the circumference to one point in the axis. In other words, you're identifying one strand that is being cut at that point in time. So therefore, N is 1. Although Vishnu asked the question, you got the answer, but I'm taking it a little bit further, where somebody could tell you, well, you know, they have N less of these little strips going out, and that's what N is, but that's not so. N is identified by the points of connection. If you have 50,000 batteries and you only connect to the terminals of one, what is the voltage? The voltage is the voltage due to that one battery, not the 50,000 batteries that you have sitting next to each other. So we clear on that. The question continues. Well, that's the part that we had to do. That's the part that was related to the bit of theory we did. All right. So again, let me just run this quickly by you again, one more time. Faraday is the one who discovered this generation effect. Faraday rotated a disk in a magnetic field and found that there was a voltage set up between the circumference and the center. And this generator is called the homopolar generator, or Faraday's generator. Now, I'm using this generator to further the understanding of Faraday's law and the theory associated with it. And what is the understanding? How come you have a voltage produced across here? The first point I made is you can consider this disk, this conducting disk, as a copper disk or a brass disk. You can consider this disk as made up of strands of wire radiating out from the middle. If we consider one strand, because I'm connecting from here to here, if we consider one strand, as that strand rotates, it will be cutting all of the field lines in this area. Faraday's law says that once a conductor is cutting the field lines, there's going to be an EMF induced. And the EMF is the amount of flux cut, which is this area, divided by how long it took for the flux to be cut. The equation is E is equal to delta phi over delta t. We worked out that delta phi is really the flux passing through that area, and the flux through any area is B by A. In this case, A is pi r squared. Why pi r squared? Because the flux lines are at 90 degrees. The flux lines are there at 90 degrees to the surface. So the area is pi r squared. And that's the numerator. The denominator is the time taken for this strand to move all the way around and come back to where it started. That time is also known as the periodic time of the revolution, and periodic time is the reciprocal of the frequency. When you put these two equations together, this is what you end up with. That's simple. Nobody clear on that? No problems. That's the derivation. Jumping from that bit of theory, a question was presented based on the same theory. All right? Sure. Actually, I'll pull that up now. Illustrator. All right. So what I said actually is, let me just go on this. This is layer 3. Lock this. I just want to put in the direction of the current, right? In the solenoid. So this the circuit is telling us the current is coming up here. The current will come up here. I'll go a little tighter. The current will come up here. I'll just hide the other layers so that it would not confuse. That's the layer I want to see. Awesome. Lock. Right. And then we layer 2. Yeah, so the current is coming up here. Let's hide everything so it's a lot easier for us to see what we're doing. The current is going up like this, right? Good. So that current that goes up here will run around the back, will be coming down the back here, and then coming back up the front. So the current again on this side will be going up. And then when it goes up, it'll come back down the back on this side and come back up. So the shortcut of this is, in all of these wires to the front, the current will be flowing up. Now, I can't do a video, but if you use your right hand grip rule and you take the fingers of your right hand and point up. All right, if you take the fingers of your right hand and point up and wrap around, the North Pole will be on the left-hand side of the coil. Everybody good? Awesome. So the North Pole will be on the left-hand side because of the right-hand grip rule. Somebody kidnap Kyra? True. Where Kyra? All right. Oh, she probably get flooded out. Internet problems. Okay. All right. So we're good so far? It is being taped. The session is being taped, so I will deposit it in YouTube for us to see subsequently. So tonight, hopefully, it'll be there. All right. So that's good? Everybody good? Awesome. You understand that question? You understand the question? Yeah. Yep. Easy, right? I hope. All right. Next part for 3 marks. The apparatus in figure 5 could be used in an experiment to verify Faraday's law by changing the speed of the motor and measuring corresponding EMF. Sketch the graph. What graph would we expect to see if we increase the rate of rotation? How would the EMF depend on the rate of rotation? Well, the equation is right here, not so. The EMF depends on the frequency, not so. So linear relationship, E is really a linear relationship with F. So if we want to sketch a graph of how the EMF varies with frequency, all we need to say is I'll just sketch a graph quickly. Change that color from a nice green to a black. You good? EMF, E. Against frequency, F. The linear function. Straight line through the origin, right? Y is equal to mx because there is no plus or minus c. E is equal to a constant by f. The question continues. Sketch a graph. State how your conclusion can be made from the graph. What conclusion? All right, well, yeah. How conclusion can be made from the graph, because as the frequency increases, the rate of cut increases and the EMF increases. I'll write that down. As frequency increases, rate of cut increases, EMF increases. Right? Also state which factors must be held constant to the conclusions to be valid. What factors must be held constant in order for this conclusion to be valid? The factors that must be held constant. The most important factor to be held constant is the strength of the magnetic field. All right. The most important factor to be held constant is the strength of the magnetic field produced by the solenoid. Secondly, what we need to keep constant is, of course, the rate of rotation. Because we're going to be measuring EMF at different frequencies. So once we lock onto a frequency, you have to keep that rate of rotation constant until we get the frequency. All right? So the rate of rotation at the measuring point, the motor, in other words, must be spinning it at a constant rate at every point of measurement. All right? That mustn't be fluctuating, in other words. All right? All right? Those are two of the more important points. The third one is not as directly linked. It's not in the mark scheme. The third one is you must keep the orientation to the Earth's magnetic field constant. You must keep the orientation of the disk. In other words, the Earth's magnetic field should not be passing through the disk, because if the Earth's magnetic field is passing through the disk, that will create an EMF on its own. this will be a small variation. And I would, under normal circumstances, neglect to say something like this because it is such a small, the Earth's field is quite weak. And because the Earth's field is quite weak, it will hardly generate much of an EMF in this situation, right? So that is why I would not even make any big deal of that. All right, so we're clear on this question. This question is completed. Anyone take a screenshot in 5, 4, 2, 1. Good. So that's the first idea on this handout. The next idea is, again, there are 3, right? I said I want the commonality seen. EMF induced in a straight wire, what we're going to use? That equation. That's Faraday's and Lenz's law. EMF induced in a spinning disk, what equation we're going to use? Same equation, looking for delta phi and delta t. This equation, looking for delta phi and delta t. And finally, EMF induced in a rotating coil, we go back to the same equation right there. All right? So that's the commonality that I'm trying to thread through the discussion this evening. The third derivation that we're going to look at is the one that you met in Form 5. You would not have met it in a mathematical form, but it is called, this EMF induced in a rotating coil is really the AC generator. Right? This is really the AC generator that you should have met in Form 5. I'm not looking at the whole detail about the AC generator. In fact, this is also the DC generator, to be honest with you. So I wouldn't put that. It's also the DC generator, because both the AC generator and DC generator, they do the same thing, except in the DC generator, you have a commutator that rectifies the AC that is being generated. They both generate AC, both the AC and DC generator. Do you know this? Yes or no? Talk to me. Do you all know this? Yes or no? The commutator is the only thing. What is this? So, annotate, clear, all right. No, you all don't know this. Right. This is YouTube. Ooh. Just a second. We'll just find the appropriate one. Just look for generator. Goodness gracious. All right, I'm not seeing a nice one, and I'm gonna waste time. But there's something here. This here shows the AC generator, where you have the slip rings. The part that I want you to look at is, if you look inside here, if you look at this, the arm of this coil as it rotates, you see the current direction changes in the coil. All right, as it rotates, you see the current direction changing in the arm as it moves. And you will say, of course that is so, because it's an AC generator. The current direction must be changing all the time. You can see also the voltmeter going to left and right. But let's look at the DC generator using the same program. This is the DC generator here. And when you look at this, all right, I want you to focus on the EMF induced here. The EMF induced right there. Now, according to our left or right-hand rule, if the field is down and the motion is to the left, the current will be induced in that direction. The resolution, this is horrible. Let's try this one. I don't know. Oh, goodness gracious. Why you figure you could look in? Oh, goodness gracious. Not at all. Not at all. I don't have time for this. Sorry. Yeah, let's go back to here. Believe me or not that both the AC generator and DC generator inside the coil and AC is produced. I will clarify this in class when I get the appropriate video, but an AC is always produced inside the coil, and whether it's an AC generator or DC generator. So I'll put AC slash DC generator, both of them. How you get a DC out of the DC generator is you use a commutator to rectify it. Now, again, I will show you that. I'm not going to invest the time on that right now. Our time is being spent dealing with Faraday's law. So the EMF in a rotating coil. So here we have a coil. This coil is, the axle of the coil is right here. So the coil is going to be rotating about that red dot. And it's rotating in a clockwise direction. All right. Now, if a coil is made to rotate with an angular velocity omega in a uniform magnetic field of strength B, we know an EMF is induced due to the changing flux, due to the change in flux linking the coil. Now, right now, at this position, we have a certain amount of flux passing through the coil. But when that same coil changes its orientation, we can clearly see that the amount of flux passing through the coil is passing through a smaller area. So here is this, all of this area, the flux passing through. So it's a big area. The flux passing through this area here represents the flux passing through the entire coil. So the amount of flux passing through the coil is in fact changing. All right. And according to Faraday's law, once there's a change in the flux linking the coil, once there's a change in the flux linking the coil, there's going to be an EMF induced. All right. The flux linking concept was done right here. When a coil is placed in a magnetic field, the total magnetic flux lines passing through the coil is called the flux linkage. The flux linkage is the product of the amount of flux multiplied by the number of turns. Is equal to flux linkages N phi. The number of turns by the amount of flux passing through. And we already know that the amount of flux passing through is given by one of these equations. Phi is equal to BA sine theta. So flux linkage is really NBA sine alpha, in this case, NBA sine alpha. So that's what we met previously, flux linkage. So here, we have a situation where we have a coil. Oops, somebody draw in. We have a situation where we have a coil, and the flux passing through this coil, phi 0 time t equal to 0, the flux passing through the coil is NBA. NB by the area when it is in this orientation is the entire area of the coil, A, all of that. It's a rectangle. Now, after t seconds, this coil would spin. The coil was here to rotate to this orientation. But the new effective area, the effective area perpendicular to the field, I should write that. The new effective area of the coil, I should put perpendicular to the field. the new effective area of the coil, that is the area perpendicular to the field, would be given by A cos theta. If this is A, if this whole face here is A, if this whole face here is A, this component or part of that face, this is the angle theta, it will be A cos theta. Again, why cos theta? Because this is the adjacent side. This part of A will be A sin theta. We don't care about that area because that's the area that no flux passing through. All the flux passing through this area, A cos theta. Are we good with A cos theta? This is A, the area of the coil. And this is the part of it perpendicular. So that would be A cos theta. Yes? It's basic vectors. The adjacent side will be built on the cos. The opposite side will be the sine. We don't want the opposite side. I'm going too fast. Going too slow. You all understand that? Yeah. Okay, good. I'm not hearing from Erin and Ashti and Jared. Jared, are you okay? Jared, you alive? All right, we're good. Awesome. So this is the area we're talking about here. So how much flux will be passing through here now? Again, what we said in this part, the amount of flux, the flux linkage is NBA here. But here, the flux linkage will not be NBA, it will be NBA cos theta. Theta is, I wrote it here, theta is the angle it sweeps out in time t. And if it's moving at an angular velocity omega, theta must be equal to omega t. So instead of calling this cos theta, it's also equal to cos omega t. T is the time it has been rotating, omega is the angular velocity. Again, that's a unit 1 equation, omega t. So the flux at time t is equal to NBA cos omega t. This is the general equation for the flux at any point, at any value of theta. And this is a little bit of calculus. The people who don't do hard math could close their eyes. E, the EMF is given by d phi dt. When you differentiate, is minus, d phi dt. When you differentiate NBA cos omega t, what you end up with is E is equal to NBA omega sine omega t. The differential of cos is minus sign. There's a minus sign here to go and deal with it. So it becomes a plus sign again. The sign doesn't really matter too much as a polarity, but just mathematically, you're okay with that. So the EMF generated when you have a coil rotating is given by this mathematical expression, E is equal to E0 sine omega t. And I hasten to add, and you need to know, that insert equation that E0, that E0 is equal to NBA omega. E0 is equal to NBA omega. And what is E0? E0 is the maximum or the peak EMF induced in the rotating coil. E0 is the maximum EMF induced in the rotating coil. So you have the sinusoidal function here. E0 is the maximum value here. The peak here, that's E0. So that's the calculus way to do it, right? Where you take your generate function and you differentiate it and you get your story sorted out. The non-calculus, imprecise, if you will, way of doing it is where you look at phi. What is phi? Phi is equal to NBA omega, NBA cos omega t. That's what phi is equal to at any time t. If I were to plot this function, with respect to time, this is what phi is going to look like. You know, I just realized something. You know, the most interesting thing is the person who suggested we have the Zoom session, Chelsea, Chelsea missing in action. Anyway, so we understand this part here. This is the EMF. This is how phi varies. Phi varies like this. The peak value is NBA. Peak value is NBA for this. Everybody's okay with that, right? This is how the flux passing through the coil varies with time. We derived this equation from this analysis, so we know where this comes from. We know where this comes from. I was just reading your comments and Helen smiling. We know where this comes from. That's the NBA cos omega t. Now, that is phi. And what do we know about Faraday's law? Faraday's law says that E is proportional to delta phi over delta t. What is delta phi over delta t? And I drew this. Let me just give you the high resolution one that I have here. What is delta phi over delta t? Well, this is not really a high resolution one, but we'll call it that. What is delta phi over delta t? This is how phi is varying with respect to time. That is the equation. That's how phi is varying with respect to time. All right. This line shows how delta phi over delta t varies. So delta phi over delta t is 0 here. It's a horizontal line. Delta phi over delta t is a gradient at any point. That's what delta phi over delta t is. This is phi against t. All right, so delta phi over delta will be the slope. So here we start with a 0 slope, that 0, that 0, and that 0 slope. And if you see delta phi over delta t is 0, it means the EMF must be 0. At every point in time that delta phi over delta t is 0, the EMF is 0. We good. Next, this here represents a negative slope. This, anytime you draw a graph on a line, looks like this is a negative slope. And E is equal to negative delta phi over delta t. E is negative delta phi over delta. So this is a negative slope. A negative of a negative gives you a positive. So from here to here, the slope goes through a variation of positive, the slope goes through a variation that is negative, but the EMF goes through a variation that is positive. Here, when the slope is positive, the EMF is the negative of the slope, so the EMF is going to be negative. So you can, without doing the calculus, you can use these two diagrams to justify that a cosine function for phi would produce a sine function for E. All right? And again, this is the equation. The peak value here, what I didn't put, and I probably will have to modify that the peak value, in fact, I'll do that right now so you'll see how I do the thing. Where is it? File, open recent. I was drawing this while I was waiting for this class to start. Open recent. Right, so what I want to do is I want to move this down. Maybe carry it across. And make it into a dashed line. Like so. And this is EMF on the axis here, but this value of EMF is NBA omega. Is NBA omega. To get omega, we have to change the font to symbol. And omega is right there. No. Omega, sorry. Group that. And yeah. So this is NBA omega. It's a peak. Of course, down here is negative NBA omega. I'm not going to put that. NBA omega, that's the maximum EMF. File. Save. File. save for Microsoft Office on the desktop. Save, replace, bang. Close this, delete this, and replace it with the new one. Right, much better. NBA omega, peak value of the EMF. Okay, so far we got that. Why is that such an important objective? Let's see what the examiners do. All right. Let me just see if I could find a question on this. There we go, right there. All right. RMS value is simply the peak value over root 2, right? RMS, that's a unit 2 objective. RMS is whatever the peak value is divided by root 2. I'm going to give you 5 minutes, everybody. 5 minutes. You have the question in front of you, but I'm just showing it here. The question starts in the previous page. Let's make it smaller. No, it doesn't start on the previous page. It starts on this current page. Okay. Yeah, it does start. Right. Here's where it starts. Figure 5 shows a coil and so on. So I'm going to give you 5 minutes to try this question. You all have the handout. That's a yes. Anybody doesn't have the handout, I will then have to put it on the document for you to see. Everybody has a handout going once, twice. Yes. Question 2008 original, part C. It's a past paper handout on electromagnetic induction. Right? 5 minutes on that. Just 5 minutes. Then I'll come and answer and we'll do a few more questions. Okay, I'm going to mute my mic for 5 minutes. Okay, I'm back. How it going? Stress? I gave you more than 5 minutes. I had to pray, so lost. Anybody there? All right, so here we go. First part, calculate the magnetic flux through the coil at t equal to 0. That's where it is at t is equal to 0. So at t is equal to 0 is the entire area of the coil. So the part 1, the magnetic flux through the coil at t is equal to 0 must be NBE, phi 0. From the handout, pretty much, phi 0 must be equal to NBE. Ooh. Right? So we have blah, 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 N. We have blah, 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 B. And they said the diameter of 0.1 meter. So if the diameter is 0.1 meter, we can work out A, which is pi r squared. A is pi by 0.1 over 2. That will give us a radius, but we have to square this. All right, so we have NB, A, straightforward calculation, and so on. Part 1. Given that the rate of change of total flux at any time is given by this, where F is frequency, they want us to find a maximum instantaneous value of the EMF. Part 2. The maximum instantaneous value of the EMF is NBA omega. This is what total flux phi. Omega is 2 pi f. The rate of change of total flux. This is how to read the question. You didn't even have to know the derivation. They're telling you the rate of change of total flux. The rate of change of total flux is also another way of describing the EMF. Right? The rate of change of total flux, as according to Faraday's law and Lenz's law, is really the EMF. So they're telling you, this is how you're reading the question, they're telling you that the EMF E, they hid this from you, right? But they're telling you the EMF E is given by this. And they want you to find the maximum instantaneous, this here is the maximum instantaneous value of the EMF, except that phi is what we already have. So therefore, what we really have to write is 2 pi f by NBA. 2 pi f multiplied by NBA, because that's what phi is. The number that you already got for this calculation. That's part 2. The maximum instantaneous value. So this is a number. You know, whatever that number is, x, that you can find. I'm not going to find it right now. The next part, this is 2, part A. That's part A. And 2, part B is where they ask you to find the RMS value. And that's the part I just said that, we wouldn't do it at this level, but the RMS value is really the peak value, E0, which is X in this case. I'll just put it as E0 still, because this is what it is. That is E0. It's really E0 divided by what? Root 2. That's what the RMS value is by definition. We'll deduce Y in unit 2, but by definition, the RMS value is the peak value over root 2 for a sinusoid. Next part. The coil, if the coil were fixed, this time you're keeping the coil fixed. Right now you're rotating the coil and the magnet is fixed. If the coil were fixed and the magnet rotated at the same rate in the same direction, what is the same rate? If you move the magnet in this direction, in other words, if you move the magnet clockwise at the same rate and the coil remaining fixed, what direction would this make the induced EMF? What difference, sorry, would this make to the induced EMF? And the answer is the induced EMF would be the same in every regard except the polarity would undergo a different change. The induced EMF would be the same in every regard except it will be E, would be the polarity would be the opposite. So if they said E was 2 pi f, if they said it was this, the new EMF would be negative 2 pi f phi sine 2 pi ft. It'll have the opposite polarity. Getting difficult to write now. I'll just 2 pi f sine dot dot dot. Negative. The important part here is a negative sign. Negative. Why negative? Well, let's analyze why. It's a little bit of a tricky idea. Now, right now, the coil is stationary. The first instance when they asked the question, the magnets were stationary and the coil was rotating. Now, I want you to follow this. In that context, this part of the coil, I'll put some color on it. This part of the coil would be moving relative to the field line in this direction. Right? That's in the first instance, when the coil itself was rotating in the stationary field. I hope you can get this idea. In the second part, you're keeping this constant, right? And you're moving this now. Now, if you are moving this, how is this coil moving in relation to this? The coil is in fact moving in the opposite direction in relation to this. Because as this moves away, it's getting further. The North Pole is getting further away. This South Pole, sorry, is getting further away from this set of the coil as this rotates, as the coil rotates. Sorry, let's back up. First case. When let's change it. When the coil is rotating in this direction, this turn of the coil is moving here. We're okay with that. And it's going to cut field lines in that range. It's going to cut these field lines on this side as it turns, as the coil turns. That's situation 1 in red. All right. Situation 2 in blue. Get it? Yeah, situation 2 in blue is where this North Pole is moving. Now, sorry, this South Pole is moving. As this South Pole moves, what is the relation of this South Pole to the same turn? It is getting further away, not so. This South Pole is getting, as it turns, is getting further away from that coil. Oh, somebody's having fun. This South Pole, as it turns, is getting further away from this strand of the coil. It means that relative to the South Pole, this turn of the coil is in fact moving like this. So it's moving in the opposite direction to when the coil was turning. And therefore, if it is moving in the opposite direction to when the coil was turning, the EMF would have the opposite polarity. Right. The EMF will have the opposite polarity. And that is what the answer is. That is the explanation. But this is an explanation you have to think through. So what I suggest you actually do is, based on what I've drawn here, based on this, again, use the blue. The blue will mean when this is moving like this. All right? That's what the blue is. That's how they're moving in blue. The red will be when this is moving. All right? And I want you to analyze that. You have to convince yourself of it, because with this remote kind of setting we're dealing with, I can't like show you it manually. The best I can do is draw it, and I hope you follow it. Okay? But the correct answer is that the polarity is going to be the same in every way, except the polarity will be reversed. Right. Screenshot, take what you need to take. It's going in 5, 4, 3, 2, 1. All right. Let's save this. Already save, and I'm not going to save this. All right, back to here. So we understand this question. We've already done this question in class. Did we do this question Friday, last week, Friday? PLV? No. All right, so what we're going to be doing in the next class is only questions, actually. We're going to be going through all of these questions in the next class. I've touched on a few. There are a couple of things. Let me just show you. In Dropbox, Hmm. All right, I will put a book for you with questions and solutions on electromagnetic induction. I'm going to do that now. Not immediately, but I have to kind of find the book. I'm going to put a book for you, Cambridge, like how you have Cambridge topical questions. You're going to have a chapter on electromagnetic induction with detailed discussion on the answers and rationale for the answers, multiple choice and long questions. I'm going to end the session. Just stop this taping.